Let's have a look at uranium. A sample of uranium ore is estimated to have originally contained 772 milligrams of uranium-238. Analysis reveals the sample today contains 705 milligrams of uranium-238. What is its estimated age? Half-life of uranium-238, 4.468 times 10 to the power of 9 years. Oh, that is a big number. Let's have a look. Let's have a look here at uranium. And it also has isotopes. Uranium-232, 33, 235, etc. Here is uranium-238. And the half-life of uranium-238. Oh my God, look at that size of that number. 4.468, 10 to the 9 years. Incredibly big number. And that's just the half-life. Let's rewrite this number, right? See exactly what it really looks like. It's 4.468. 10 to the power of 9 means I have to move that decimal place over 9 times. 1, 2, 3, 4, 5, 6, 7, 8, 9. Here's the new decimal point. 0, 0, 0, 0, 0, 0. Putting in the commas. And there and here. There are the hundreds of thousands, the millions, 4.468 billion years old. So uranium-238 has a half-life of approximately 4.5 billion years. And the half-life is an average. So it's about 4.5 billion years for the half-life of uranium. Let's have a look at the age of the Earth. Doing an internet search, the age of the Earth today is estimated to be 4.5 billion years old. And that's just the half-life of uranium. Oh my God. So the age of the Earth, 4.5. Or 3 billion years old. Now you may say that, well, the age of the Earth is determined by the half-life of uranium. Well, maybe, and maybe not. Scientists do use other means of determining the age of the Earth. Consider. And I mentioned this once before, and I thought this was timely, that I received this their Scientific American in April 2020 issue. I thought it was a timely issue. The new view of the Milky Way. And within it is, again, artist's rendition of our Milky Way. Various other renditions with the 4 arms. I talked about this before. But if we look within it, within the article over here, and it says here that the Milky Way probably would have been recognizable as a large galaxy about 5 billion years ago. So the Milky Way is basically 5 billion years old, or recognized as a galaxy about 5 billion years ago. Conversely then, by using this data to determine the age of the Milky Way, we could also interpret the age of the Earth, about 5 billion years. And there you have it. And uranium has been with us all that time. And it will be with us a whole lot longer yet. At just a half-life of 4.5 billion years. Incredible. Well, let's carry on with the word problem. We are dealing with amounts, or masses. Therefore, we need to use this equation. N is equal to n naught e to the minus lambda t. Let's write down a list of what is given. I'll do that here. N is today's sample. N being 705 milligrams. N naught, the original amount of uranium. This is mass-wise, it's 772 milligrams. Lambda, ln of 2 divided by the half-life. And that becomes ln of 2 divided by, now this half-life is such a big number, I'm just going to leave it as it is. 4.468 10 to the power of 9 years. And lastly, the term for time, and that is what we want to find. We have what we need. I'm going to leave lambda as is. It's a matter of taking all of this and plugging it into our equation. In doing so, I'll do that here. And a 705 milligrams is equal to n naught, 772 milligrams, e to the power of minus. And lambda I'm going to use as ln of 2 divided by 4.468 10 to the power of 9 years times the time, which is what we are looking for. I'm going to divide both sides by 772 in order to isolate E. If you were to take the ln of both sides now, the way it is right here, you're going to find yourselves in a world of mathematical hurt. So let's make it easy on ourselves and go 705 milligrams divided by, because everything here is multiplied, like this, divided by 772 milligrams is equal to e to the power of minus and the exponent ln of 2 divided by 4.468 10 to the power of 9 years times the time. The milligrams and the milligrams cancel out. Now we can take the ln of both sides. Ln of 705 divided by 772, keep that in brackets, is equal to the ln of that whole term, e to the minus ln of 2 divided by 4.468 10 to the power 9 years, and everything times t. Having done that, we're going to bring the power down, and I'm just going to use another page for that. Ln of 705 divided by 772 is equal to, bringing down the powers, it's minus ln 2, everything divided by 4.468 10 to the power of 9 years times t. And then we have ln e. In a previous video, I showed you that ln e is simply 1, so we can ignore it. Solving this now for t, multiplying both sides by this denominator, it would look like this. Ln of 705 divided by 772. This is a number, I just haven't done the calculation. Multiplied by, and this is the denominator, I'm going to bring it to the top on the left hand side, 4.468 times 10 to the power of 9, and the unit goes with it is years, is equal to minus ln 2 times the time. Bringing ln 2 over to the left hand side, 705 divided by 772 in brackets, 4.468 times 10 to the power of 9 years, divided by the minus ln of 2, is is equal to the time. Now let's do this in our calculator. And the reason I'm doing it this way is because that is such a huge number. I'm going to let the calculator do the work for me. Following the proper rules of bed mass, let's clear this. Doing this ln first. Ln, open bracket, 705 divided by 772. Close that bracket. And that's equal to, I'm going to multiply that times this number, 4.468 exponential 9, and press that equal sign. And it's a negative number. And I'm going to divide by minus ln 2. Divided by minus ln 2. And press that equal sign. And that number is 585, 207, 872. And the unit is right here, years. Time then is approximately equal to 585 million years. Going back to the original word problem for significant figures, we have 3 sig figs here, 3 sig figs for this measurement. 238 was given to us as 4 sig figs, so we need to use 3. 1, 2, 3. And 1, 2, 3, and 1, 2, 3 years. Therefore, the estimated age, estimated of this particular iron or uranium ore is approximately 585 million years old. 585 million years old.